Hi, welcome to United Astronomy Clubs of New Jersey. We are here on site in Jenny Jump State Park in Hope, New Jersey. I think I saw a car just coming in getting parked, so I'll give them a couple minutes to get walking down here and settle down in a seat. But I do want to welcome everyone who's not only come here to join us, but also who are joining us online, because that's right, we do live stream this on both Twitch and YouTube. So if you're ever looking for something to do on a Saturday night and you haven't come here, do look us up there, join us in chat, say hi, hit those like, follow, subscribe, free actions. If you want to be extra nice, hit the ones that cost money. We are a nonprofit, but that's never expected, always appreciated. That being said, I do want to encourage everyone to check us out on our website. uacnj.org is where you're going to find a whole bunch of information, such as a list of all our upcoming talks, as well as information on our member clubs, because we are actually an organization made up of other astronomy clubs, therefore the United Astronomy Clubs of New Jersey. And one of the easiest ways to get into astronomy and most accessible ways is to join your local club, check out what they're doing. You can also check us out on our social media, our Facebook, Instagram. We have a Discord server, all great places. If you have questions, you need some help with your brand new telescope rig, feel free to reach out to us there. We're always more than happy to answer those questions to the best of our ability. That being said, not all of us are astrophysicists, astrophysicists. That sounds wrong, but it's probably right. So sometimes the more technical details will trip us up, but that's besides the point. Still feel free to ask those questions. We do have people we'll reach out to, like Lindsay here. So, since it looks like most people have found a seat, I do want to go over a few safety things. If you need to use the restroom, that is the porta potty in the back. It is to my left, your right. It is big, it is blue, it is dark, so it is illuminated by red for ease of finding in said dark. We also have a little museum and gift shop area. I'll be manning that after the talk because they do not allow me to break the laws of physics and be in two places at once. Apparently that is strictly not allowed, much to everyone's dismay. Normally, what you might have noticed when you have come in, we have multiple sheds over there. Each shed is actually its own observatory where the roof rolls off and houses its own telescope. On a night where we're not expecting rain, normally we have those roofs open and we have you able to look through the eyepieces of those telescopes. Which ones depends on which volunteers we get, because not all volunteers are trained on the same telescopes. That being said, I think we will have a couple of those observatories open, so at least you can see the telescope setups here. When we finally go to leave, we do want to use our headlights. We do not like getting run over. I'm fairly certain most people also agree with that opinion. One of these days I'll put a poll, and I guarantee you that there will always be that one random person that will be like, yeah, no, I want to. No, let's avoid that. That being said, even though we are using our headlights and we can't really control where those point, when we are using any handheld lights, like a flashlight, lantern, or cell phone, do try and keep those lights pointed towards the ground. We do want to try and limit the amount of blinding of people we do at night, where it ruins their night vision. Even though we all want to try out that brand new 100,000 lumen monstrosity we got off of Amazon, like I said, pointed towards the ground. But you are not here to listen to me ramble on for forever. You're here for Lindsay. Lindsay Goodwin is a physicist Yep, I said that right. Specializing in plasma physics in the geospace environment and coupling from the sun to the earth. Lindsay received their Bachelor in Science in Physics at the University of Calgary in 2005, their Master in Science in 2014, and their PhD in 2018. And those were in physics and engineering physics at the University of Saskatchewan. Afterwards, they went on to fill their postdoctoral research positions at Boston University and New Jersey Institute of Technology before being awarded the Jack Eddy Fellowship, which is the NASA Living with a Star program in 2020. They are now an assistant professor at the New Jersey Institute of Technology. And with that, here's Lindsay.
Okay. Ah, okay. Hello. I'm gonna go fix it. Excellent. Okay. Cool. Thank you all so much. I'm very excited to talk to you all. The dorky way of talking about my talk or trying to, give a summary of what I'm talking about is to say remote sensing in the geospace environment. But that's not the goal of my talk. The goal of my talk isn't to use scary terms and stuff like that. It's to get you to understand what I do and why plasma is cool and why radars are cool and all this fun stuff. But yeah, I'm super excited to talk to you all. So I'm going to start off with kind of a weird question of like, do people know what light is? Anyone? A wave? That's really good. That's controversial, depending on how you're going to think about it. But yeah, I guess like the simplest way I would describe light is like some sort of wave of like a packet of energy. So we typically think of light as being some kind of electric field and magnetic field that are like waving together. And through that, you have like energy that travels and propagates through the air. But there's different kinds of light. We can talk about gamma rays, which are kind of light in that they're a type of electromagnetic radiation, which are kind of like these scary thing that people are like, oh, that's associated with like nuclear power plants and stuff like that. We can talk about X-rays, which will tell you if your bones are broken. Ultraviolet, the scary stuff that comes from the sun. Visible light, which is the way that I can see you all and you can see me right now. Infrared, which people typically think of as heat. Microwaves, which, cook food for us, as well as radio waves. The thing that like is in our car that like kind of over time people are listening to less and less and instead want to listen to like iPods. That's not true. Anyways, their own music from YouTube and blah, 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 blah. I wanted to show this to indicate that like as we go from gamma rays all the way to radio waves, we get less and less energy. So radio waves are great because they're like low energy, not super scary, doesn't like cook us or anything like that. But I also want to show that like as we go from one side of the spectrum to the other side, our wavelengths get longer and longer and longer. So when we're talking about gamma rays, we're talking about very, very, very little waves that are the size of like nuclei. But as we get to radio waves, we're talking about waves that are the size of like skyscrapers and mountains and stuff like that. I'm not sure if people really play with their radios that much anymore, but have you ever gone like on a drive and you go into a valley and like your radio is like, yeah? That's basically because the radio signal can't get to your car anymore because now you're down way too low and the hill that you're going down or the valley or whatever is now blocking the radio wave. Yeah, I think that's the main thing I wanted to hit there. So one of the ways that we communicate with each other is through radio waves, but also this kind of applies to like cell phones and microwaves and stuff and all that goodness, all GPS receivers. But I decided instead of trying to like have a complicated diagram with every way that we communicate with radio waves, I decided to just use emojis because, they're free to use. So here, let's say I have a radio transmitter, which is transmitting radio waves. And here I have a radio receiver that is picking up radio waves. All good? Cool. All right. Now let's say I turn them on. I now have electromagnetic radiation traveling from the transmitter to the receiver. Good. All right. What happens if I move them farther apart? Does it stop working or does it still work? Yeah, it's still fine. Like I can still transmit radio waves from the transmitter to the receiver. No issue. What happens if I move them so far apart that now the Earth is in between my transmitter and my receiver? So here, for example, I have a transmitter way over there and a receiver over there, but the Earth's curvature makes it so I can't have a direct link anymore. So like, how would I, in that case, communicate with someone who's over the horizon? And that's like a very practical problem these days of like, what if I want to call my friend who lives over the horizon? What if I want to talk over the Atlantic Ocean? What if I want to talk over the Pacific Ocean? Sometimes, what if I want to talk to someone in Antarctica? Well, this was the perfect problem for physicist Marconi. So Marconi, he was from 1874 to 1937. He was alive during that time. He was an Italian inventor and electrical engineer, best known for developing the first practices and practical systems for long-distance radio communication. There he's featured with his sidekick, and together Carl, Carl, his friend there. I don't know, I'll call him Carl, why not? They won the Nobel Prize in Physics in 1909 for being able to transmit a radio signal across the Atlantic Ocean. So basically what they did was in December 1901, Marconi set up a radio transmitter in Cornwall, England, way over there. And then over in Newfoundland, he set up a radio receiver, which really was like a giant kite that he flew up, like, and the kite itself, like the wire that was holding down the kite, was the radio receiver itself. And what he saw was that, like when he basically told, or like he had, at a coordinated time, he was like, okay, people in Cornwall, I want you to just give me 3 dots of like a Morse code. And in December 1901, he received that signal. I want to say that, like, even though he was using a kite and the kite did go quite high, if I was to try and directly see Cornwall from Signal Hill in Newfoundland, I would need a kite that goes up about like 400 miles. In order to directly have that radio communication link with that. Marconi did not have 400 miles worth of wire. He instead had 600 feet, or 0.11 miles. So the question is like, okay, if I couldn't directly see the receiver, or rather, like if there's a transmitter and I'm not directly looking at that, how am I able to receive that signal? And plasma is basically the reason. That's the big takeaway I want, is that like plasma is cool. So let's talk a little bit about what plasma is and why it's cool. So here I have a lovely picture of plasma. This is also known as the pillars of creation. I think that this was taken with the James Webb telescope, and you can see that there's all these like cool structures and stars and gases and all this fun stuff like that. We can also look at the star cluster. I think it was also taken with James Webb, but like there's a bunch of other sort of like spacecraft that they had looking at the same region to like be able to form this picture together. We got cool stuff like ring nebula that look like this. And we just have like the general universe where we can see that there's a bunch of plasma. And of course, at this point, you're like, well, wait, like, what are you talking about? What actually is the plasma in here? So I decided to put a little arrow so you all know where the plasma is. It's here. So here we have plasma that's full like throughout the universe. So to take a step back from that, plasma, as we think of it, we usually think of it as the 4th state of matter. The reason why it's called this is William Crookes back in 1879 was playing with cathode ray tubes, and he identified this like kind of gas that would like react in a certain way to electromagnetism and waves and fun stuff like that. And then Irving Langmuir was the one who actually gave it the name plasma, because he was like thinking of it as like kind of like the thing that's in our bodies. It reminded him of blood for some reason, that like how it was like fluid and moved and stuff like that. More technically, what a plasma is it's a quasi-neutral assembly of free electrons and ions. So people know electrons and ions? Yeah, kind of. Like you have charged particles where it's like electrons, which are overall thought of as negative, and then you have positives, which are overall thought of as positives, and you have positive and negative, and they like to attract. If I have 2 negatives, they repel, or if I have 2 positives, they repel. It's the same idea. It's a gas that has a lot of these charges. It's just that like what's special about plasma is that over a long distance, electromagnetism will be able to propagate. So we say that the rules for something being a plasma is that it's quasi-neutral, and it's an ionized gas where charges move freely and interact via long-range Coulomb forces, blah, 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 blah. Basically, you have long-distance kind of reactions when you put an electric field or a magnetic field in here. I put in this dorky diagram here that's just kind of showing a map of like the plasmas that we know about in our universe. So I'd like to point out that there's like industrial plasma. Oh, that doesn't work. In the center-ish, there's industrial plasmas that we make in labs, and like people down at Princeton will be like, oh, I have like this accelerometer that I'm confining plasma in, stuff like that. We also have fusion related like nuclear stuff. We also, so you look further and further down, we have interplanetary. The interplanetary medium has a lot of plasma in it. We have the solar wind, which we're going to talk a little bit more about in a bit. And at the very bottom, we have interstellar. But one thing I want to highlight is that there you'll see Earth's ionosphere. And I want to point out also that Earth's ionosphere, people think of like plasma as being a really hot thing. And I think that's because like when we go from like a solid to like a liquid to a gas, people think of like things becoming hotter and hotter. And then they're like, oh, fourth state of matter, plasma, that must be really hot. But your lowest temperature plasmas are about like 116 Kelvin or minus 250 Fahrenheit. So they're quite low in stuff. And Earth's ionosphere is pretty close to that. Like it's this like cold plasma relative to the rest of the universe that like exists near us. So then the question is, okay, what is the ionosphere? Where is that on Earth? Is that in the ground? It's not in the ground, it's in the sky. So the Earth's atmosphere is full of this plasma that's just very simply generated by the sun reacting with neutral particles up there and creating ions and creating electrons. Remember those positive charges and those negative charges are the things that like to attract or the things that like to repel. How this happened is just from simply like photons hitting the upper atmosphere and like interacting with that. Depending on where we're at in the atmosphere, we'll have different kinds of plasmas, like ones that are made from oxygen or N2, like nitrogen, two nitrogens, or like a molecular oxygen as well. And this is just kind of a plot of like this is a cartoon. This isn't super realistic, but it's basically showing that between 70 kilometers off the ground, here it puts it at 400 kilometers, but like you can see plasmas way up to 1,000 kilometers off the ground. Does that all make sense? Sorry, I'm very like pro-interaction, otherwise I get scared and anxious. Is everything okay? Good, okay, very good. Thank you. So plasma is generated in the atmosphere from photoionization in the sun. However, the sun does this other thing with the Earth's atmosphere that sounds a little bit scary, but it's not too scary. We all know the sun. Yeah? Okay, cool. We generally, when we look at the sun, but don't actually look at the sun because that, use like something safe to look at the sun. We think of it as like kind of like a uniform surface. But if you look at the sun in like different wavelengths and lights and stuff, you can actually see that sometimes there's a lot of structure that's sitting on the sun. So here we have a picture of the sun. Have people seen the smiley sun? So these were co-rotating interaction regions is what they're called, or rather they're kind of like these cold spots that have like these weird magnetic like signatures associated with them. And they just so happen to look like a cute smiley face. But I'm sure people have heard of like solar flares or solar storms. No? Yes? Okay, cool. All right, thank you. So these things, like the sun in general, will release plasma out into the universe. And with that, a magnetic signature of the sun is carried out into the beyond. However, when we have like the smiley sun, or recently there was like, it looked like Tasmania. There was like a giant like Tasmania sort of island sitting on there. When we have those structures or flares or sunspots or all this crazy thing, we get these structures that move out in the solar wind out towards the Earth. And then what's kind of scary, but not too scary, I'm not trying to scare people, is that this solar wind will start to interact with the Earth's magnetic field. So what I'm trying to show here, let's look at the diagram on the left first, is the solar wind carries with it a magnetic field or an interplanetary magnetic field, an IMF. For the sake of keeping things simple, we're going to pretend like that's always pointing south. That is absolutely not the case at all. So as this interplanetary magnetic field moves closer and closer towards the Earth, it starts to see the magnetic field of the Earth. And at a certain point, they'll collide together. There'll be lots of magnetic tension and pressure and all this cool stuff. But at a certain point, they'll merge together. And we call this day-side merging. So going from step 1 to step 2, that's showing day-side merging, where the solar wind merges with the magnetic field of the Earth. Then it moves. It still has that inertia from the sun. The sun's a pretty big thing. And it's releasing a lot of plasma. And so those magnetic field lines are pushed away from the Earth. So moving from 1 to 2 to 3, we're moving anti-sunward, away from the Earth. But the magnetic field lines of the Earth are being dragged, like anti-sunward as well. So we move from 3 to 4 to 5. Then at a certain point, which is way, way, way further out than what this diagram shows, it's about 30 Earth radii sometimes, the magnetic field and the interplanetary magnetic field will wave goodbye to each other and they'll pinch back together, and then the geomagnetic field will move back towards the Earth. In other words, we have this huge sort of magnetic field that moves the magnetic field of the Earth from the day side to the night side and then back. So we go from 1 to 2 to 3 to 4 to 5, and then you see that picture flow, which is the magnetic field moving back towards the Earth. This GIF that I have here is just trying to show the pinching mechanism that happens when the magnetic field, these two magnetic fields merge together. I actually think that this GIF is a little bit better in showing that. And so what we're looking at here is the interplanetary magnetic field collides with the magnetic field of the Earth. And then we see this kind of like sweeping of magnetic field lines out towards the night side, but then like some kind of movement back towards the Earth. So it's this large scale, we call it convection, even though that's not the correct word. Maybe we'll call it flow of magnetic field lines moving. And once again, like these extend really, really far out, like 30 Earth radii. Sometimes the moon gets caught up in these interactions, but don't worry, the moon's fine. It's okay. It's okay. But these magnetic field lines map down to the Earth and move plasma around in the Earth's atmosphere. So plasma doesn't really like to move perpendicular to the magnetic field. It's a weird property that it has. And so it will do anything it can to not change like which magnetic field lines it's attached to. So we have this magnetic sort of like convection that causes plasma to move around. So in this diagram, I'm just fully going to step in here. Over here is where magnetic field lines from the day side map down to the Earth. However, then we have the magnetic field of the solar wind and the geomagnetic field will connect together and will push plasma from the day side of the Earth to the night side of the Earth, just like this. So at very high latitudes, also known as the polar cap, we have plasma that moves from the day side to the night side. Then at lower latitudes, down here, we see that the interplanetary magnetic field and the geomagnetic field go their separate ways. They're still friends, but, you know, say goodbye for now. These magnetic field lines will sweep around around at lower latitudes here in this region that we call the auroral region. Have people heard of the aurora? Yeah? Okay, so it's that merging and unmerging. That's one of the things that's really contributing to the aurora. We'll come back to that later. But we have this oval here where we have aurora that's very common, and it's because of these magnetic field lines moving around and pinching and all this fun stuff. All right, so I talked about the Earth's atmosphere, and I talked a little bit about radio waves, but I haven't really connected the two yet or proved that like they actually have some sort of relationship with each other. So the Earth's atmosphere has moving plasma or plasma moving around. How is this important for radio waves? It's because they like to dance to the radio. Plasma really likes moving around when it like sees a radio wave coming at it. It'll get very energetic and excited and start dancing around. This is probably like several weeks worth of a course that I'm trying to condense into one slide. If there's any questions about it, please ask me, but I will do my best to explain this. So basically this top picture here is showing like different charged particles above the Earth. So what we have is we'll have ions that like to drift around with magnetic field lines. They'll gyrate around. They kind of like spin around magnetic field lines. Even though they're still moving with the magnetic field, it's kind of like they're doing sort of like a buzzing that's still moving in a certain direction. And electrons will like to also buzz around as well. So we have ions and electrons that like to buzz around magnetic field lines. But when you push a plasma, it doesn't like to be pushed. And will start to restore itself. And so if I went and I pushed a spring, it's very similar to a spring or like a mass on a spring. Plasma won't like that. And it'd be like, hey, I don't like being pushed in this direction. I'm going to go back to where I was. But it'll kind of move back too much. And then in that case, it's like, well, wait a minute, this wasn't where I started. I started over here. I'm going to bounce back. Oh, no, now I'm too far. And it'll start like bouncing back and forth like this. And this is kind of what radio waves do to a plasma is they shove it, or rather dance with it. That's a nicer thing. Let's stick with the dance theme. It'll dance with plasma and move plasma back and forth, very much like a spring. So plasma gyrates along magnetic field lines, but it also has a natural frequency that it likes to oscillate when it's disrupted. We call this the plasma frequency, and it kind of determines if radio waves can propagate through or if radio waves bounce off it or all this cool stuff like that. When radio waves interact with the plasma, it can redirect the signal. It can also show us signatures of plasma physics. I feel like at this point, this talk is very dense, and I apologize for that. But let's look very quickly at some of the ways that plasma likes to dance with radio waves. So using bounced radio signals, we can see plasma in the sky, and we can also see how fast it's moving. So one of the things that we do quite frequently is we send radio signals up into the sky to talk over the horizon. Or we'll bounce multiple times off of the ionosphere in order to communicate with someone really far. And that's what this diagram here is trying to show, which I worry the people in the back cannot see this, so I'll try and describe in as much detail what's going on. So here we have a radio tower, and we have radio signals that are bouncing off that. So here this radio tower sends a signal up, but then it bounces off the ionosphere and comes back down. If I lower the elevation a little bit more, the signal bounces off of this part of the atmosphere and comes down. And that's basically how we can have long distance communication, is that we're bouncing radio signals off of plasma that just lives in the atmosphere. So plasma redirects radio waves by changing the index of refraction in the atmosphere. People might have heard about the index of refraction. It's basically the reason why you'll see instances of this, for example, where someone's in water and their head might be shifted off, or you put a pencil in water. Water's the thing that's coming to mind right now. You'll see there'll be a little bit of shift. And that's basically what's happening in the atmosphere, is that it's shifting radio waves and bouncing them across the ocean or something like that. And that's how Marconi was able to send signals over the ocean, was basically he was bouncing them off the ionosphere. He didn't entirely know what he was doing at that time, but he had a dream, and he went after that dream, and he was pretty successful, won a Nobel Prize. So follow your dreams, you might get a Nobel Prize. So one of the things that we do in the space physics community is okay, well, if we can bounce radio signals to talk to someone really, really far away, could we use radio signals to also tell us something about plasma? And that's basically what we do. And one of the main instruments that I work with in order to be able to see plasma within the sky, which keep in mind plasma is invisible, is we use SuperDARN, which stands for Super Dual Rural Radar Network. It is a silly name. I love it. So what they do with that is using radio waves bouncing off of plasma, we're able to see where and how fast plasma is moving in the atmosphere. So this is a network. You can see a bunch of these different fans here. There's about 22 of these huge systems. This is on a farm that bounce radio waves off the sky, use the information that comes back to it, and is able to say, hey, there's a plasma over there. It's also able to tell you how fast the plasma is moving, where it's going, fun stuff like that. So this is a picture here from January 2003. This was during a geomagnetic storm. And what I want to indicate here is you can see that there's these fans here. This is a top-down view of the Earth. So here's Canada, here's Russia. And you can see that there's these kind of stick and ball sort of pictures. Where these lines are pointing or showing, where these lines are pointing is where the plasma is going. So what we have here is a snapshot of how plasma is moving in the atmosphere. So here we see that there's a motion this way and across here and all this cool swirling that's going around. But keep in mind that one of the reasons why we do this is to see how the sun is interacting with the Earth and how how the solar wind is, mixing up the atmosphere for us. It tells us how these two things communicate with each other. Another thing that we can do with radio waves is we can see how dense the atmosphere is. So one of the things that we can do is using disrupted radio signals, we can do that to find plasma as well as see how dense it is. Everyone here has a cell phone? Yeah, okay, cool. Everyone here knows how to use GPS on their phone? Yeah? Okay. So GPS works because there's a whole bunch of spacecraft that are in space that are making connections with your phone and basically locating where you are. However, this doesn't happen too often, but sometimes during very strong geomagnetic storm, a patch of plasma will move between you and the spacecraft, and your phone won't know where it is because it can't make that link with a spacecraft. So I included a scary line there. Oh no, it can affect power grids and stuff like that. But in this picture, which I'm totally standing in front of right now, we can see that there's these spacecraft that are trying to make a link with a receiver that's on the ground. But as they move into this patch of plasma, the signal becomes distorted. That was very loud there. Oh, it was because I was on the speaker. That's good. We can see that there's like these loss of lock moments that we have. However, it does change with frequency. So one of the cool things that we also do is we're like, hey, if we can see how a plasma is interacting with a signal, and we kind of have like a bunch of different signals to see how this plasma interacts, we can start to determine what kinds of plasma we have, how dense are those plasmas. And I like to show this plot here. Have people heard of like the May storm, the geomagnetic storm that happened last year? No? Okay, there was a huge geomagnetic storm, like something that doesn't happen all that often, like once in 10 years or something like that. What this plot here is showing, you can see that there's different continents and fun stuff like that. But because GPS receivers are so cheap and easy to like distribute in places, we have all these GPS receivers that are on the ground that are measuring how dense is the plasma between the receiver and the spacecraft. I'm going to run that again. Whoop, or not. Does that run it again? There we go. Cool. So this is 24 hours of GPS receivers measuring how much plasma there is. You'll remember I said like photoionization is the reason why we get a lot of plasma in the atmosphere. So over here is the day side, and I can see that because it's a lot of red. Here's kind of more the night side because it's darker. But at a certain point, you'll see that like this plasma is drifting around, and that's just because the sun is rotating. But very soon, you start to see that it gets very, very dark as like a solar storm is hitting us at that time. This not only led to like enhanced plasma in the sky, and also like a lot of like agricultural issues because people who like navigate their combines with like GPS signals, they couldn't make those locks. So we can see that there was all this enhanced plasma here that made it difficult for people to know where they are, machines to know where they are, and to have those different communication links. But was great for science because we're able to see all this cool stuff going on here. Yeah. The other thing that we use radio waves for is looking at plasma physics in the ionosphere. And boy, I really wanted to give like a huge talk on this, but it is very nuanced and sounded very boring the more I started putting slides in here, so I reduced it down to one slide. Have people heard of the Arecibo facility? Yes. Okay. No? I heard some yes and some no's. So in Puerto Rico, a few years ago, it recently crashed this like centerpiece here. We had this huge radar that was located out there. Here's the giant dish, and we were able to steer it using like this giant platform. You might be able to see a tree there just to kind of give you the size of this. This was this massive instrument. And what it was able to do was to send radio signals up into the sky and back down. You could do cool things like actually look at the moon and look at the topology of the moon and how like dense craters were and fun stuff like that. This also became a telescope for a few times, or rather like people were using it as a telescope because it was so good at listening for radio signals. But what we can do is we can bounce radio signals off of the atmosphere, and if we're listening very, very, very carefully, we can see the signatures of plasma physics themselves within the atmosphere. Oh, sorry, I saw like a comma moving, and it was a moth, and I was like, get back there, you comma. Anyways, so high-powered sensitive radar, such as the Arecibo radar, can tell us about small frequency shifts that are tied to plasma physics. So in this diagram here, which there's a lot going on with this diagram, this is time. So as we change with time, these are frequency offsets. So like just very small like frequency shifts that are in the signal. And these colors here indicate how much power we're getting back. And you'll see that like there's these weird kind of like structures or kind of ghosts that are existing in here. So this middle line here is the ion line. And it's a reflection of kind of like the ion density that we have and the motion of ions. The thermal motion that we have in the atmosphere. We also have these gyro lines here, which remember when I was talking about like plasma gyrating and like ions buzzing around magnetic field lines? That's a signature of that. We also have like other plasma lines down here. There's cool stuff that we still, like this was written in 2010. We still don't know what this is. So we're still trying to figure this out. Like Arecibo was a very valuable radar system that like, even though it's been gone for a few years, we're still trying to figure out what was it that it saw and what does it mean when we have like those weird kind of bumps and signatures in there. This is just showing in a little bit more detail, like kind of like the signatures that you see. Really, you don't have to look so much at this. This is more the cool stuff of like all these like dips and frequency changes and power that is going up into the atmosphere and bouncing back down. The other thing that we can do, and like this will be the last thing I talk about, is we can listen. to radio signals that are like up in the atmosphere. I've talked a lot about like sending radio signals up and then looking at the signal that's come back. It can get a little bit more complicated than that though. So we're going to take a quick detour and we're going to talk about the aurora. I'm not sure how many people have seen the aurora, so I'm going to play this video here. But this is from the International Space Station as it's moving over top the planet. And we can see that there's those green structures in there. We can also see that there's little cities that are moving under and all this fun stuff like that. And you can see that there's these giant waves that are the aurora that's in there. So this, I think, actually is the aurora australis. I believe that this is a pass over Australia. However, like you'll remember from before, I was talking about like the auroral oval and like charged particles and fun stuff like that. So basically, when we have particles that are stuck on magnetic field lines, sometimes they'll shoot down into the atmosphere. They'll become so energized that they shoot down and create the aurora. And that's basically how we get the aurora, is through energization of particles. Explore Earth. I will. So charged particles gyrate and bounce around magnetic field lines, and when they become energized, they fall into the atmosphere, creating the aurora. They don't always fall down. Sometimes they'll stay there and they'll become more and more energized through a bunch of different mechanisms, like waves that like are generated within the magnetosphere, or like or rather within the magnetic fields of the Earth. You can also have lightning that sends energy upwards. Like we think about energy coming down, but like really this lightning is so strong that they shake the magnetic field of the Earth. And one of the cool things I want to talk about is like, sure, yeah, we can bounce bounce radio waves off of plasma to like hear it, but also we can just put instruments in plasma and just listen and see if we hear any radio signals. So I'm gonna exit this for a second. So there was these cool missions. This cool mission called the Van Allen probes, which was able to hear these different kinds of things when it went up there. It was specifically using some instrument called the emphasis, which is looking for radio signals. I wasn't able to get my computer to hooked up to audio, so I'm going to try and use the microphone to like really broadcast this. So this is what Van Allen heard when it got out into the magnetosphere and into the radiation belts where a lot of energetic particles are. Can people hear that? Yeah. And then, so those are called chorus waves, and the reason why is they sound like birds. And so we call them like chorus waves. They're a signature of some kind of physics that's going on within the radiation belts and the magnetic field of the Earth. Another one is Whistler waves, and I like this one because this is lightning, and we know quite certainly that this was lightning. So this is what lightning and the radio signature of lightning interacting with plasma, there we go, in the magnetosphere sounds like. Can people hear that? It gets really active here. So that's what lightning sounds like, as you all know.
I do want to ask you if you could give me those links after the presentation. I'll add them onto the YouTube description.
Okay, sweet. I think that was Kimberly, but I'll just pretend like there's a ghost living around me. But anyways, the whole reason why I wanted to give a talk was to demystify a little bit of like space physics and radio physics and stuff like that. Really the thing that like is super cool is that we can use radio waves to not only like look at plasma that's really, really far away, but we can look at like use radio waves to like hear plasma dancing and being, you know, active and existing in certain places. So using radio waves, we can look at plasma in the geospace environment. All the stuff is in the geospace environment. And this tells us not only about the plasma physics that's happening to our Earth, but it tells us about like how our Earth couples to space. So I'd like to give this talk here because like astronomy is awesome, but it's also kind of remember that we are a part of it, and we're a frog. Oh. No, it was going to help me give the talk. But it also tells us about like our home and the environment and like how we are connected to like outer space. And I like closing on this quote from Carl Sagan. People know about Carl Sagan-ish? Yeah, I love Carl Sagan. And one of the quotes that he has is, "The surface of the Earth is the shore of the cosmic ocean. On this shore, we've learned most of what we know. Recently, we waded a little way out, maybe ankle deep, and the water seems inviting." And I love that, and I feel like that's basically what I study is the shore of the universe. But yeah, that's all I wanted to talk about. Thank you very much for your time, and let me know if you have any questions.
All right, so we will be doing a question and answer session. Thank you so much. We got this working. If you want to put it on and then turn it on, otherwise.
I'm fine using that.
Well, they're going to use these for questions.
Oh, okay. Fair enough.
Okay, so we are going to be doing a question and answer session. How that's going to work is for people here. You're going to raise your hand and kind of wave it about because I am like the Jurassic Park T-Rex. If you stop moving, you cease to exist. You're just a shadowy figure in the dark. Which is why it's easy for me to catch the frogs. They keep moving, trying to escape. Online people, you have it easy. You get to just type in chat, and I do know we had a couple questions in chat. Okay, so before we get into that, I do know a couple of people snuck in after the safety briefing, and that is inescapable. If you need to use the restroom, that is the porta potty to the back. It is to my left, your right. It is large, it is blue, it is illuminated by red because it is quite dark in the state park. We do have a little museum area and gift shop I will be manning after question and answer session. I think we may or may not have an observatory still open where you'll be able to peek your head in. I don't know if online people can hear, but people here can definitely hear that it is raining, so we aren't going to be opening up a telescope because we do not need the rain ruining any sensitive electronics. That being said, when we go to leave, we are using our headlights because we prefer not to get run over. But any flashlights or whatnot we're using to move around in the dark, such as if you might want to go see the view off the rock over there. Do try and keep those lights pointed towards the ground so we don't accidentally blind people. All right. I'm going to start this off by our first online question was, isn't plasma technically really hot, or is there also cold plasma?
First of all, is this on?
It should be.
Help me.
It's on. It says.
Okay. Hello. It's like lighting when I talk. Hello.
It's on now.
It's on now?
Yeah.
Okay. All right. Cool. The question was, is plasma technically hot?
Yeah, they thought plasma was hot. Is there also, if it is there also cold plasma, or?
Absolutely.
There's confusion on the temperature of plasma. Maybe there's multiple different types of plasma with multiple different types of temperatures.
So, like, we think of plasma as being hot, I'd say for, like, two reasons. Number one, it's got the name of, like, the fourth state of matter, which is a cool name. Oh, is a cool name. I'll talk more quietly. It's a cool name, but,
He muted the...
Oh.
Because we were trying to
Fair enough.
troubleshoot.
Okay.
Thank you, Chris.
Thank you, Chris. So yeah, we want to think of like plasma as hot. I think because it's the fourth state of matter, and so people are like, oh, it must go from solid, liquid, gas to plasma as you heat it up. However, and also because plasma does exist around like very energized things, like we have like tubes of like plasma. Oh, like those plasma spheres, which are kind of like this hot, heated sort of like gas. However, a lot of plasma does exist down to like 116 Kelvin or minus 250 Fahrenheit. Just basically because a lot of plasma is in the interstellar medium. of like the universe. So I would say that like actually a lot of plasma is quite cold. And the Earth's ionosphere is getting a little bit warmer than that. It's like 1,000 Kelvin and stuff, as opposed to, I will say on the hotter end of the spectrum though, we have, let me not get the zeros wrong, it can go up to 1.2 billion Kelvin. And that's pretty hot.
Just a smidge.
Just a little, yeah. So yeah, I hope that answers that question.
Bit higher than the tanning beds you find. Was there a question out here? I thought I saw a hand. Either that or someone was.
Okay. Haha.
Haha.
A question about aurora. Why does it keep changing colors, and what is really determining the colors?
Oh, I might have this slide. Okay, this might be a lot of disappointment. Hold on a second. Do I have it at the very end? Oh no, I deleted it. No. Okay. The reason why plasma will be a different color, aurora will be different color, is basically you have energetic particles that like fly down into the atmosphere and hit a certain neutral. And basically, what neutral it hits will change the color. So if you see like a purple aurora, that usually means that you're looking at nitrogen. If you see red or green, that usually means that you're looking at something that's been, that the atomic oxygen has been hit. Depending on the color as well, you can tell like how like energetic that precipitation was. I'm saying precipitation, but that's just energetic particles flying into the atmosphere. Does that answer your question? Yeah. Oh, thank you.
Right. So I'm going to skip one of the online questions. I'll get back to that, but there was a follow-up to that last online question. Is it accurate to describe any ionized gas as a plasma? Is a candle flame responding to a strong magnet because of intermediate ions in the reaction? And are those ions considered plasma regardless of temperature?
You can have a lot of different kinds of ionized gases. You could have a gas that's just a bunch of ions, or you can have a gas that's just a bunch of electrons. What makes a plasma is that it's quasi-neutral and how it carries magnetic fields. So like there are other kinds of like ionized gases out there, but the most plentiful is actually this kind of like quasi-neutral sort of thing where you have the same amount of like ions and electrons that are there. Yeah, I don't study candles as much though, so I won't comment on that. But that's what makes a plasma is that it has a similar amount of like positive charges and negative charges, and how it reacts and how, I guess to get a little bit more detailed, you have like these shielding effects that happen within plasma where basically it's hard to see any charge because like protons and electrons are so good at like moving around and like shielding each other. Or rather like ions and electrons are so good at like moving around and shielding each other. So yeah, no matter where you measure it, it'll be basically quasi-neutral. I hope that kind of answers that.
I hope so, because
was that too much?
Science was never my forte. They put an art major and emceeing the science program.
I guess to answer my question, to answer the question, not my question. There's lots of different kinds of ionized gases, but a plasma is a specific kind of ionized gas.
All right.
Yeah.
Was there another question out here? Bueller?
Hello.
Hi.
Is there a standard way to turn something into a plasma? Like, for example, water. If I heat it up until it's a gas and then do something to it, can I turn it into a plasma?
I wouldn't say that there's a standard way. Like in the stuff I do, like I don't turn anything into plasma because, like I'm dealing with radar signals that are measuring plasma. I don't like generate plasma. You can do funky things like that, but that's just not what I study, and that's like a whole other sort of science. But yeah, not really like a standard way. Like it's just basically what you want to do is you want to create a bunch of ions and a bunch of electrons, and there's a lot of different paths to that. Yeah. Does that answer your question? Yeah. Cool. Thank you.
Yeah, she's working with all natural plasma. but if you can't find all natural plasma, store-bought will do.
I love that.
Right, so I'm gonna go back to that online question I had skipped over. They said they know you said you can bounce radio waves off plasma. Could you use the plasma itself to send information?
I've never thought about that. That's
Or is it too random?
that's interesting. I guess
we got her into the next science project.
well, like now I'm kind of wondering, like, are they talking about like put a signal in plasma and then move the plasma? Or are they talking about that's really cool? Like okay, kind of maybe. So I guess like what I'm thinking about, and like this is me just kind of off the records thinking about this cool question. Is that we can send radio signals to actually no, I got an answer. Okay, cool. So we can all right. There's this cool research that's being done where basically we're trying to like energize plasma using like other sort of radio signals. But wait. Like, so you can use like radio signals, you can use rocket burns to like energize plasma and like create waves and stuff like that. And like kind of through that, you can look at the signatures of that plasma. But it's never been like complex enough that like you could put like a secret message like, oh, I really think your shirt's cute today, like in the plasma or anything like that. It's basically like you can see evidence of like rocket burns and other sort of like human influences on plasma. But yeah, it's not overall like complicated enough to like actually give a message.
Yeah. I don't know how to phrase that better. I don't think we're necessarily putting plasma into the phone lines and being like, haha, it's now better than this is fiber 2.0 made of plasma.
Well, okay, actually I'll go a little bit more detail, but then I'll stop about it. Like, okay, so like one of the things that you can see in plasma is like the signatures of like radiation belts and like charged particles that have fallen down. So like there are like ways that like you can energize plasma, or like kind of like hypothetical ways that like people are thinking about. I'm wording this kind of vaguely about like how you could energize plasma that's already trapped in like the upper atmosphere and stuff, and how to get that to come down. And maybe that's like a cool way that you could send a message. I don't know. Anyways, sorry, I'll stop. That was very interesting. Thank you, whoever that was.
All right. Any online people, if you have any last minute questions, do get those in. I want to give them a couple minutes, because by the time they receive that message, since stream delay is a thing, we'll already be like 2 minutes into the future. Were there any other questions out here? I know we have a lot of crickets, which is why I have to be careful of the toads escaping.
I'm so worried that I've like stepped on a toad during this talk.
Usually they're pretty good about not attacking your feet.
Okay.
And not
so
being
the attack
underfoot.
toads are out tonight.
Yeah, that was 2 presentations ago where one just kept jumping up my leg. That was kind of unpleasant. So our next online question was, will anyone do a facility like Arecibo in the future? They believe they said they would not be rebuilding that particular one.
I have like a lot of like kind of personal feelings about that, because like when Arecibo, I didn't really emphasize this, but like when it fell, it was about 60 years old. And like when you have a facility that's existing for that long, like it's like also like a community, if that makes sense. So like there's people who like are in the space physics community who became really attached to like this cool thing. So like it's a little bit like not like, I don't know, it's kind of like a gooey emotional sort of subject. And people have wanted to rebuild it, but like there's also kind of I guess long story short, TBD. But I guess like the questions that like people are thinking about are like, okay, this facility was existing for 60 years. Is there more new science that can be done with it? If like we build a new one, is it going to be exactly the same?
I would imagine the people who worked at Arecibo knew some of the fun quirks, to put it lightly, and said, and hopefully they'll write it down like next time, let's move this over here, because it was a very bad idea, and made it.
There's things like that, yeah. But also it's like, okay, if we're gonna make that improvement, then let's just make an even bigger dish, or like one that's more powerful. One thing I'll kind of highlight, and I'm getting way too much in the details, is like because this is like how this was designed, it's only able to look in one direction at a given time, but we have more sophisticated radio techniques, so we can actually look in multiple directions. So it's like, okay, should we build this exactly as it was? Should we build it as something different? If this has been existing here for 60 years and we got a lot of data, maybe we should build it somewhere else. Yeah, so long story short, I don't have a good answer. I hope something fills in now the gap at the equator, because we actually don't have any really good radars down at the equator, or like ones that are, I should say,
Publicly
easily
accessible.
Yeah, actually, yeah. Like, there's ones that like you have to know someone in the Navy to get like information from, or the Air Force. This one, like, the data is still like just open and available online for anyone who wants to like play around with it, which is super cool. But anyways,
Cool. The next online question is, how many frogs is Kim up to? The answer is 6. Kim has prevented 6 toads from entering the museum area.
they just really want to get in the museum, and you're stopping them.
The,
and, like,
the thing is,
just let them learn. No, I'm joking.
we have some lights in there because humans can't see in the dark. Dark vision is not a thing for humans. So we have light. Bugs like light. Frogs and toads like bugs. So we get frogs and toads. That being said, I like to keep them around, so I just keep scooting them that way. Because I like the things that try and eat the things that eat me. Like the mosquitoes that last week could carry off a small child. You're laughing because you know what those mosquitoes look like. Right. So, any last minute questions from out here? Because it looks like we're done with the questions online. I do want to once again thank everyone who has joined us here and in our online chat. Do check us out on our website. All the information, a link to this presentation will be up there. Like I said, I'm going to grab those links from you to put it in the YouTube description. So that online people can hear the blippy things.
Yes, yeah. Whistler waves and chorus waves. Yeah.
Yeah, it sounded like laser frogs. Back on the frogs thing. But like I said, those will be out there. If you have any questions, specifically on this presentation, feel free to drop those in the comment section. I do check those. So if you have any questions you just weren't able to get out or thought of later, feel free to drop them there. Or like I said, on any of our social media like Facebook, Instagram. We got our Discord server, all great places to ask those. And with that, thank you everyone. Have a good night. Clear skies and good seeing.
Thank you all for coming out.